Okay, good evening. Starting chapter 11, and 11 is about area, which you probably know something about, quite a bit about. A very important topic in geometry, so we will delve into that. The first point to make about area, and this actually is a postulate, and that is that if I have any closed region, then there is area associated to that. And the area is the amount of surface that is bounded by that region. So you can see in that the red is my area. So we have areas of circles and areas of all of our quadrilaterals. Again, anything that's bounded whatsoever. As long as it's a bounded inside and an outside to the region, why then it has area. So this chapter we're going to be finding the area and using area in problems. So the area is bounded by the region. Okay. Alright, now looking at the units that we measure area in, let's look at a couple of examples of tile. Maybe you've got tile in your bathroom or tile in your kitchen. I've got 3 examples of tile here. The first example there on the left is round tile. Okay. And you can see here it is simply round pieces of ceramic tile that fit together. The next one are oblong shapes that are fitting together. And then the third one over here are some nice squares. Clearly the squares fit together the best, don't they? They what we call tessellate a surface. That means they fill in all of the space on the surface very nicely. That is why we tend to use square units when we talk about area. We will use squares to represent the amount of surface that a boundary takes up. We would not use circles because we have these gaps here that are not being accounted for if I were to use circles. Or these oblong shapes would be a difficult unit to use to explain how much surface, because we've got some that are small and some that are large. But squares fill the plane very nicely. And from this, so now we're going to use square units. Square units that are made up of distance measurements. So if this tile here was, this could be an inch by an inch, this then would be 1 square inch. If this tile here was a foot by 1 foot, so a foot by a foot, then that would be 1 square foot. We can see very clearly why looking at a rectangle, for example. So here I'm going to look at a rectangle. That's our first shape that we're going to define the area for. If I were to ask you how many tiles does that rectangle capture, you would say, well, I've got 1, 2, 3 tiles up and 1, 2, 3, 4, 5 tiles over. 5 times 3 must mean there are 15 of these inside here. And you would be right. What did we do? We took the length, that's how many tiles in the length, times the number of tiles in the width. We also use, if we don't call it length, a lot of times we'll call it the base, and we'll call this the height of the rectangle. So the area of a rectangle is equal to the base of the rectangle multiplied by the height. Okay. We'd also look at, let's look at a square. Here I'll draw a square on these tiles. We can see here that a 3 by 3 square has 9 square tiles in it. So we can see here that a square, this was 3 times 3 equals 9. So the area of a square is equal to the side, whatever the side length is, squared. In that case it was 3 times 3. Now, you should probably keep in mind the relationship of quadrilaterals in the taxonomy. Do you remember that when we drew the taxonomy, we had a rectangle, and we had a rhombus, and those together, a square was both a rectangle and a rhombus. And all of the properties of the rectangle were imputed onto the square, and all the properties of the rhombus were given to the square as well. And we said if it is a square is always a rectangle, and a rectangle is sometimes a square. And so we can see here that the property of a rectangle, in that its area is base times height, will also apply to the square, because a square is always a rectangle. And so we could use base times height for the square as well, and we just know that the base and the height are the same value. So that's why we can just get along by saying it's length side squared. Okay? So what we should learn from this is our unit of measurement is squared units, because they define the space or the area that a region is taking up. Let's look now at some application. Okay, so here's maybe it's a room in your house. Okay, lots of application of area all around us. Okay, let's look at the flooring, for example. Flooring is the nice wood flooring there. You might go to the store and buy wood flooring for $4 per square foot. Okay, and you would buy it by the square foot, because the square foot is how we would measure how much we need. Right? Similarly, let's look at the wall, the paint there. A typical gallon of paint might say 400 square foot per gallon. If I knew the area of my wall there, if I knew the area of this wall, whatever that area would be, in some square feet, I can divide that by 400 square feet to get how many gallons I would need to purchase in order to cover the wall with paint. Again, the whole point here is that we have a unit there that is area squared. Let's look at the pretty green wallpaper there. Pretty green wallpaper applies area. Let's suppose I wanted to have somebody install wallpaper. They might charge me by the square foot, because they're putting it on a surface bounded by the edge of the wall. So this might be 30 cents per square foot. And again, just like before, if I wanted to calculate how much is it going to cost, well, I would take the entire wall, and take my area, take the area of the wall, which is going to be in square feet, and I'm going to, in this case, now I'm going to multiply it by 30 cents per square foot. Look at how my unit analysis is going to shake out when I multiply these my square feet are going to cancel, and this will be left, this will give me a dollar amount. So the area of the wall times 30 cents per square foot is going to give me the cost there. And this is, let's see here. This is you right now, right? Putting your feet up, watching, big smile, because you're having a great time. Okay, let's move on. You see certainly some application. We're going to get into that application in this chapter and in the next chapter, okay? An important postulate. Postulate says, if two closed regions intersect only along a common boundary, then the area of their union is equal to the sum of their individual areas. Wow. All of that to say, we should be able to calculate areas of interesting figures, such as the one given, and breaking it down into perhaps simple rectangles. So this shape here can be made simpler by looking at the area of this region and the area of this region and the area of this region and finally the area of that region. And now the task would be to, assuming that all these are right angles, these are rectangles here, and finding this. Well, this is a 6 by 2. That must be 12 centimeters squared. Be sure to put your units on here. I have to be somewhat clever about figuring out these distances here on the next one. AJ is 7. So what is this length here? And so we're going to have to think critically about what my measurements are. I've got HG here. I can tell that my entire distance, ED, let's see, ED is 3. EF is the 6. This 6 plus that 2. Oops, I'm sorry. Not that 2. But this 2 here, that's 2. 6 and 2 make 8. So that should be an easy 24 centimeters squared. Here I've got BC is 2. And this height here, how do I figure out what that height is? Okay. Well, AB is 5. This is 5. And I know I have a total of 8, so that must leave 3 here. So 5 plus 3 is 8, so 3 times 2, this is 6 centimeters squared. Alright, and now I've got 8 units for this guy, 8 units for that one here, and let's piece this together. This is 2, this is 3, that leaves 5, this distance is 2, AJ is 7, AJ is 7, so that leaves 5 for this distance. See how I did that? Just breaking all this down and finding out my lengths is all I'm doing. 5 times 8 now is 40 centimeters squared. So to apply this postulate, if I've got a closed region and they have common boundaries, so these are closed, these are 1, 2, 3, 4. I've got 4 regions with common boundaries. If I want to know total area, all this is saying is that I sum them. So the total area is 12 centimeters plus 40 centimeters squared plus 6 centimeters squared plus 24 centimeters squared. And that will be my total. Now, a point that I want to make here is that you're going to want to get especially clever at finding areas and finding dimensions. I just went about this problem the long way. but it is the most common way that a student would tackle this problem. But the cleverest of the bunch would do this. They would recognize that this is one big rectangle. They would recognize it as one big rectangle. And then they would take that entire rectangle, which they know to be 8 by, here I've got 12, right? 8 by 12, and they can find that area. And then they would subtract out this area here and that area there. And they would subtract that out because they know that this has got to be 4 centimeters squared, and this one has got to be 10 centimeters squared. And you'll get the same answer as before. Okay? So the moral of the story here is take these parts, take these shapes, break them down, find individual links for rectangles, find the areas, sum them together, or be clever about your addition, be clever about your subtraction. Here's another example to kind of drive that point home. Here's another example to drive that point home. So, in the world of packaging, area is money. Soda can packaging company looks at the area 4 cans take up, how much area is wasted. So if I'm in packaging soda cans, I've got these circles there, and how much area is wasted. The area that I'm speaking of is this area here. That wasn't good. Okay. This area here is wasted. This area here is wasted. Think about it as material in the packaging that really doesn't serve a purpose except for just needs to kind of be there in order for the rest of it to make sense. All of that area is what I'm calling wasted. How do we find that area? Again, be clever with your subtraction. We know how to find the area of a can of pop. According to this drawing, this data here is 2.5 inches in diameter. So if that's 2.5 inches, this is a radius. It is 1.25. So that means I can find the area of a can. Area of a circle is pi r squared, which is pi times 1.25 that quantity squared. Alright, so that's the area of that. Now, I have 4 circles. So I've got 4 circles, so that's going to equal 4 times pi times 1.25, that quantity squared, is my area of the circles. Now, let's find the area of the purple. To find the area of the purple, okay, I'll mark this in red. I found the area of these. To find the area of the purple, I must first find the area of the entire package. This entire package. So what's the entire package make? Well, we need to know this height. Remember that this was 2.5, and that is 2.5. So together they make 5 inches. And this is 2.5, and this is another 2.5. So this distance here is another 5 inches. So my square is equal to 5 squared, or 25 inches squared. Therefore, my waist equals the 25 inches squared minus the 4 pi times 1.25 squared. That's going to be how much waste I have. Okay? And you can take that and get a decimal approximation. I'll let you do that on your own. And something else that we will be talking about at a later date will be the efficiency of this packaging. And to look at efficiency, we look at the ratio of the red area, in this case, to purple area. The area that we need, that we're using, to the area that it tends to be waste in the product, in the packaging. That would be efficiency. Okay, so something to kind of think about. All right. Finally, number 6, one last postulate. Congruent figures have equal area. Okay, so congruent figures have equal area. These two figures are always congruent, okay? And the area of the yellow is down here at 14.59 and red, and obviously they are the same. Okay, so you can imagine that's going to be something that we're going to draw upon in certain problems as well. So with that kicks off area. Our whole chapter is going to be about area. By the end of the chapter, we will have a bunch of area formulas, so you're going to want to be very careful with your notes and copying those down clearly. You want to have those memorized. You want to stay up to date on those as we go through the chapter. Okay, so with this, I'll sign off. Have a great night, and see you in the morning.